This video starts off the lessons for Chapter 5, which covers factoring and algebraic fractions. This video and subsequent ones will discuss the following objectives that you see here. Finding the greatest common factor, identifying and factoring the difference of two squares, factoring a square of a binomial, factoring trinomials, methods of grouping, and then adding, subtracting, multiplying, and dividing algebraic fractions. So let's get started with section 5.1, which is special products. And this is just a review of the things that we talked about in chapter 1 when we come to multiplication. Just kind of a review of the law of exponents. An exponent means that you have that whatever that number or variable is, that base, you have it that many times and you're multiplying them together. If we have a number to an exponent times the same number to another exponent, so we have the same base in both of these cases, then all we need to do is add the exponents. If we are dividing, then we subtract the exponents. A lot of times it's easier if we want to keep positive exponents to say that if the numerator has the higher exponent, then we end up with the numerator exponent minus the denominator exponent. And if the denominator has the highest exponent, then we subtract them as well. We do the denominator minus the numerator exponent. But we keep it in the denominator because it ends up being a negative exponent. If we've got a base to a power and then to another power, then we can just think about that as being that base that many times again. So we can multiply the exponents. We can distribute an exponent over multiplication and division, but not addition and subtraction. So we can only distribute an exponent over multiplication because that's what an exponent means. It means to multiply. And since multiplication and division are inverse functions, then we can distribute an exponent over either one of those functions, but not addition and subtraction. Because addition and subtraction do not mean multiplication, we can't distribute that exponent. The last two here, we know that anything to the 0 power is 1. You can think of it this way. If you have a to the n divided by a to the n, well, anything divided by itself is 1. And if you use that law from number 3, you subtract the exponents, you get a to the n minus n, which is a to the 0. So that is why anything to the 0 power is 1. Likewise, we already kind of talked about this with number 3 as well. If you have a base to a negative exponent and we want to write it with a positive exponent, then we would put it under the fraction bar with a positive exponent. So one thing to keep in mind is that a negative exponent is not going to change the sign on your actual number. It is only going to move it to the opposite side of the fraction bar. If it's in the top, then you move it to the bottom. If it's in the bottom, you move it to the top. But you do not change the sign of the number itself. A quick review of some of the other products that we talked about in Chapter 1. The difference of perfect squares. So if we have, for instance, x minus y, x plus y, then if we were to FOIL this out, we would get x squared. The outer term would be plus xy, the inner term would be minus xy, and then the last term would be minus y squared. So that plus xy minus xy is 0, and we are just left with x squared minus y squared. And this is what we call the difference of perfect squares, because we've got a perfect square here, we've got a perfect square here, and we're taking the difference of them by subtracting. Another one that is helpful is if we have something like x plus y quantity squared, and this is, like I said, we cannot distribute an exponent over addition or subtraction, because what a squared means, what an exponent means, is that we have x plus y times x plus y. We have that whole thing times itself, which means we need to FOIL. So remember what an exponent means. You can't just distribute it whenever you want. You have to remember that it means you multiply whatever this base is that many times. In this case, we have 2. So if we FOIL this, we end up with x squared plus xy, and plus y squared. And if you simplify that, you end up with x squared plus, we end up with 2 of these here, so 2xy and then plus y squared. If this had been a negative, then the only difference would be this would be a minus 2xy in the middle here. So those are 2 common ones that we see. And again, we can use the formula for the perfect square trinomial to expand these without having to FOIL them. And so in this case, we would take the first piece squared, so the 2x, so we would have 4x squared, and then we would multiply them together, we would get negative 6x, and then we double that to get negative 12x, and then we square the last one, which is a plus 9. And so that's using that formula from definition 2 to expand the perfect square trinomial here. So pause the video now, see if you can figure out number 2. So for example 2 here, if you square the first one, you get 9a squared x to the 4th. For the second, if you multiply these together, 3 and negative 7 is negative 21, and then you get your a, x squared, and z cubed. So when you double that 21, you get negative 42, a, x squared, z cubed. And then you square the last one, so you get a positive 49, z to the 6th. As far as squaring a trinomial, if you have a plus b plus c and you want to square it, then you would take a plus b plus c times a plus b plus c. So when you multiply these out, you end up with your, when you distribute this first a, you get a squared plus ba plus ca. Then you distribute the b, you get ba plus b squared plus bc. And when you distribute the c, you end up with ca plus cb, or bc, plus c squared. So this all simplifies to be, you've got an a squared, a b squared, and a c squared. And then you end up with 2 of each of the other things. You get a BA, and a BA is going to be plus 2, we'll write it as AB. You get a C and AC, or CA. So you get 2 of those. And then last but not least, you end up with a BC and a CB, which would be 2 of the same things. It doesn't matter which order they're in because we're multiplying. So if we have a trinomial squared, then we take each term squared, then we also have to add 2 times each of the combinations. So 2 times AB, 2 times AC, and 2 times BC. So let's see if we can use that formula here. If this gets too complicated for you, you can just go through and FOIL it out. That works as well. This is just a shortcut to kind of help you. So in this case, we end up with the first one squared, which would be 2x squared plus negative 4y squared. And notice here that I put the negative inside the parentheses so that we know to square it, plus z squared. Then we have to do double all of the pairings. So we have plus 2 times 2x times negative 4y plus 2 times 2x times z plus 2 times negative 4y times z. And notice that I put a line through my z so I don't confuse it with the 2's. Okay, so if we simplify here now, we end up with 4x squared plus, because the negative squared would be positive, plus 16y squared plus z squared. So all of these squared terms should be positive since we're squaring them. And then if we multiply here, we've got 2 times 2 is 4. 4 times negative 4 is negative 16 xy. So these terms can be negative because we're not squaring anything. And then we get plus 2 times 2 is going to be 4xz. And 2 times negative 4 is going to be negative 8yz. So that ends up being our final answer for this expanded form. So I want you to pause the video at this point and work example 4. So for example 4, when everything was expanded out, you should have ended up with 9a squared plus 4b squared plus 25c squared minus 12ab, because we got 2, negative 3, and 2. 30ac, again the negative 3 and the negative 5 would give you positive 15 times 2 is 30, and a 20bc, 2 times 2 is 4 times negative 5 is negative 20. The last thing that I want to discuss in this section, and we already covered this in chapter 1, is dealing with a binomial cubed. And we talked about Pascal's triangle and how we can use that for any binomial to a power. So we did a few examples with binomial cubed, and we'll do a few more here. So with a binomial cubed, again, if you recall, you end up with a plus b cubed. So if you wanted to, you would have to multiply this out, a plus b times a plus b times a plus b. And in that case, you would have to FOIL these first two together, and if you did that, you would end up with a squared plus 2ab plus b squared. And then you would have to multiply that again by this a plus b, and you would end up with an a cubed plus a squared b plus 2a squared b from this piece plus 2ab squared when you multiply it by b, and then this last term you would get plus an ab squared and a b cubed. So all of that simplifies down to be the formula that we had in the last section, which is a cubed, then you've got 1 plus 2 of the a squared b, so you end up with 3a squared b, and then you get 2 plus 1 of the ab squared, so 3ab squared, and a b cubed. So again, the formula for this is that you end up with the first term cubed, then you end up with the coefficients 1, 3, 3, 1. So then you take the first one squared, so the a squared, 1 of the b's, then you decrease it, you get 1 of the a's and 2 of the b's, and then you end up with b cubed. So again, it goes a cubed squared 1, and as far as the b's are, you end up with b squared, b cubed. And again, if you add up the exponents for any given term, you end up with 3. You've got a cubed, a 2 plus 1, a 1 plus 2, and a cube. So let's see if we can try this on example 5. So we're going to start with the x here, so it's going to be x cubed plus 3 times x squared times 2y plus 3 times x times 2y squared plus 2y cubed. So again, you're kind of swapping out terms. Every time you get rid of an x, you add in a 2y. So every time you get rid of the first term, you add in a second term. So in this case, this simplifies to be x cubed plus 3 times 2 is 6, x squared y. In this case, you end up with 2 squared, which would be 4 times 3, which would be 12x y squared. And then 2 cubed would be 8y cubed. So again, pause the video here for a second, try this next example, and then resume the video when you've simplified it. So for this example, you should have ended up with a final answer of 64x cubed minus 240x squared plus 300x minus 125. So again, be careful with these. You had a negative in this case, so that just comes with the second term. Negative 5 here, negative 5 here, negative 5. That's your second term. So be careful with the signs here. It's just easier to remember one formula. Some people teach the plus and the minus. I find it's easier just to remember the one formula and remember that if you have a term that's negative, then that just comes along with it. Okay, we're going to do one more example here, and that is to expand. We've got an x squared times this binomial cubed. So in this case, we need to expand the binomial cubed first. So we're going to have x squared out front, and then if we cube this, we've got 1 cubed plus 3 times 1 squared times negative 4x plus 3 times 1 times negative 4x squared plus negative 4x cubed. So again, we're just using that formula, first one cubed, then 3 times the first one squared times the second, plus 3 times the first one times the second one squared, plus the second one cubed. So again, the x squared just comes down until we get to the point where we can multiply it through. 1 cubed is 1. In this case, 1 squared is 1 times 3 times negative 4 is negative 12x. Negative 4 squared is 16, positive 16, times 1 times 3 is going to be positive 48. And then we end up with an x squared from the x squared term there. And then if we cube this last one, negative cubes remains negative, so we end up with negative 4x cubed. The last thing we do here, since we have this x squared out front, is we distribute it to everything. So we end up with x squared minus 12x cubed plus 48x to the 4th minus 64x to the 5th. So that concludes the lesson for section 5.1. Now go on to the homework and do the homework for this section, and then go on to section 5.2.